you're on.
Alright, I'm Chris Wright. I'm a senior in the Associate Electrical Program here at VTC. And I'm here to introduce you to the Wright Charger, which is the project. Yeah, next slide, please. So the last few years, solar energy has been one of the big things on people's minds, trying to find an alternative energy source. So the first photovoltaic energy was first discovered in 1839 by a guy named Alexandre Edmond Picard, when he found that shining light onto an electrode that was submerged in conductive material actually produced current. And then in 1941, the first solar cell was made by Russell Ohl, using certain metals that produced electrons when they were exposed to light, and then other materials that accepted electrons when they were exposed to light, and then putting a conductive material between the two gave us solar cells. Next slide. So this is my system diagram. I decided to make a solar USB charger for cell phones or other small electronics. So I got my solar panel, just diode protection that goes to the board, but also goes to, actually it's going to be two AA battery packs that both connect to the board, so even when there's no sunlight, the USB can still charge the phone. So my USB is going to be here, and then the solar panel gets plugged in there, and the battery packs are going to be plugged in here. So these are the first two designs that caught my eye. This one uses a buck boost converter that's made by Texas Instruments. And this one's just kind of crude. It's just got a toggle switch here and then batteries here. So it just switches between charging the batteries or charging the USB. But this one also, I like this idea here. It's got a resistor divider for 2 pins on the USB. The 2 middle pins are data pins. And iPods and I believe certain other small tablets need those pins to charge them. And then another idea I liked was this diode here is here for protection of the battery in case somebody puts the batteries in backwards or something. It prevents the negative voltage going into the circuit, which could potentially ruin stuff. So I ended up using the diode idea, the resistor divider here in my implementation, and also the battery pack idea, just in case there's no light, you'll still be able to charge your phone. St. Dennis recommended Linear Technologies, which they excel in making these little buck boost chips. So I emailed them. I was going to ask them for some free samples, and one of the ladies there actually sent me an article by this guy Jim Drew, who did a lot of background research on using these chips as solar panels. And he used the LTC 3652, which actually it improves the efficiency on solar panels because solar panels are rather inefficient. And actually it has a thing on it where it can, when VN falls lower than what the load needs, it reduces the charge current by reducing a control voltage across the inductor. So it actually increases the efficiency. Alright, next slide please. So here's the basic buck circuit, and here's a basic boost circuit. The difference between the two, the main difference is where the inductor is. If it's on the left side of the switch, it's a boost. If it's on the right side, it's a buck. And how those operate is when the switch is off on the buck, there's nothing happening on this side. But when the switch opens, current starts to flow. It slowly increases across the inductor because it cannot change instantaneously. So the voltage becomes whatever it needs to make that current happen. And it ends up making a lower voltage than what you put in. So that's how you get the buck circuit. And on the boost circuit, when the switch is open, current is flowing, this side will be positive, this side will be negative, and current will start flowing across the inductor, creating magnetic field. And then when you open the switch, the impedance rises, so the magnetic field gets destroyed, and the current will want to start flowing, but it doesn't want to change instantaneously, so it'll create a higher voltage on this side. After, I forgot to mention this, but polarities end up flipping, so the current flows the opposite direction. It'll end up creating a higher voltage than what you put in, which gives you your boost circuit. And this is part of the block diagram from the LTC 3129, which was recommended to me by Linear. But it uses 4 switches and 2 capacitors and inductor to create both of these in one. Alright, next slide, please. So this is the whole block diagram for this chip. It's really got a lot in it. It uses this logic switch here, or logic chip here, which both of these switches go down to the logic switch, and it'll decide whether it needs to buck or boost. The other thing I wanted to touch on in here was these 3 pins here, various combinations. You set them, you connect them together and connect them to VIN, and it'll give you a corresponding V out. Hold on. The other 2 ones I want to talk about are the run pin here and the MPPC pin. The run pin, it's actually the start for the whole thing. Once it's above a certain voltage, which it's usually set to 1.1 volts. So when it gets higher than that, it'll enable VCC, which enables the whole chip. You can also program it using these this resistor divider here to be a certain voltage. And I didn't put the equation on here, but the equation for that would be 1.22 volts times 1 plus is it R3 over R4, which those aren't labels, I can't tell you which ones those are. And then there's the MPPC pin, which this chip will do what the LTC 3652 will do. Whereas you can set this voltage to a certain point, and if the voltage drops below that, then it'll regulate the voltage on the inductor to give you more current and voltage out. Alright, next slide. So this is the size of the chip I got here. This is the LTC 3129-1. This was just a thing that came, that it was like a plug to the package that this thing came into. I put it in there just for example of the size of it. And as you can see, it's many times smaller than that dime. And then this is the table for programming V out using those 3 pins I was telling you about. You connect them certain ways and it'll give you different voltages. This is the one I'm using since I want 5 volts out. I'm connecting 1 and 2. Oh, it's not the VN, it's the VCC, sorry. But I'm connecting those 2 together to VCC to get my 5 volts. And then this one gets connected to ground. Next, please. So this is just the solar panel that I got. It's a 12 volt, 210 milliamps, giving me 3 watts. Thought it was relatively cheap, so I ended up getting it. It's from All Electronics, which I don't know too much about. Seems like a relatively good design. So this is when I breadboarded my circuit. It's just huge mess, there's wires everywhere. I ran into an issue. I ended up burning this chip out by accident because I was trying to look at the waveform on the inductor with an oscilloscope, and I neglected to remember that there are these pins here, the 2 pins that the inductors connect to. They can only handle a minus voltage of like 0.6 or something, so I'm guessing that I applied too much voltage at the pins from the oscilloscope or something, and it ended up burning and smoking out. Next slide.
So you had a spare, of course?
Yeah, one of them. So this is the block diagram again, and then this is my schematic. As you can see, there's only a few components that I actually needed to add to the circuit. So I wanted to show this with my schematic. There's two capacitors, one for VN, one for VCC, and those are both here. And then another one for Vout, which is here. And then the capacitors and inductor for the switches is here. And then I put that resistor divider from that other circuit right here for the USB, so I can hook it up to iPods or other kind of tablets that need those two data pins to enable the charging. Alright, next slide, please. And this is the board layout, what it's actually going to look like. Actually, I am going to reduce the size a little bit here, maybe do something, pull this up or something. But the DIP adapter is going to end up getting plugged in here. Because the chip is so small, the machine, it can barely cut out the traces that you need to for this. So I put in these so I can just either plug it in to connectors or just solder it right in, which I think I was just going to solder it right in. And then all these capacitors, well, not these two, but this one, and this one need to be close. Because if they're too far away, it creates a lot of EMI, and the chip doesn't like that a lot. Also, this inductor needed to be really close to the pins. I mean, there's still going to be some extra, just because of the size of the pin lengths on the other side of the adapter where they attach. But I tried to put it as close as I could without causing too many problems. And so again, the solar panel will get plugged in here, and then my battery packs will be plugged in here. And this diode here is protecting this battery pack from people putting in batteries backwards. And then this diode here is for protecting the solar panel, so current doesn't flow back into it. Alright, next slide, please. So I had a huge issue with soldering this onto the DIP adapter. It came with this nice stencil, which was awesome. It made my life a lot easier, but I think I put too much solder on the chip, and the solder was kind of old and outdated, so when it went into the oven, it splashed a lot. So I had to use a toothbrush to brush in here between the pins to try and scrape as much solder as I could off. And between the oscilloscope and the solder, the extra solder on the chip, it could have been either that burned the chip out when it did. And when I hooked it up to test it, it wasn't acting the way it should have. It was just kind of acting like a voltage divider. It was just lowering the voltage a little bit. Alright, next slide, please. So some other issues is when you're all the components that they recommend, they're all surface mount. Because the VCC, the Vout, and the VN capacitors all need to be a low ESR, and also like microfarads in size. They recommend all surface mount components, which is hard to do up here. Another issue is the LTC3129 is really easy to break because it's so small. You could squish it really easily or lose it. Also, another issue is a lot of the traces, like the Vout and VCC, they need to be short and wide trace lengths. So you need to put them as close as you can, but the trace lengths also, or the trace widths also need to be really large, so it could potentially make some issues with building layouts. And again, the specifications on the input-output capacitors and also the inductor, they really all should be surface mount, because if you compromise and use like a ceramic or something, you could end up losing efficiency on the chip, which you can get up to 95% efficiency if you use what they recommend. Alright, next. So thank you, St. Denis, thank you, Jeremy. Also thanks to Ralph Esposito and Bob Marceau and Mark Correo for teaching me all these years and filling my head full of all this knowledge to use. And thanks Bob Royce for building circuits building boards over and over again. He actually helped me a lot when it came to soldering the chip on my DIP adapter and all that fun stuff. Any questions?
For the sake of the visiting team, can you explain to them the difference between a buck and a doe?
Yeah, you shoot the buck.
Oh,
as
sorry, I
soon
mean
as
a
you
buck
see
and
it.
a boost.
Well, the buck and the boost, it depends on where the inductor is. The diode gets placed in a different spot too, but mostly it's where the inductor is, either on the left side of the switch or on the right side of the switch. If it's on the right side, it's a buck, and if it's on the left side, it's a boost. When it's a boost, when the switch is open, the current will just flow between in a clockwise manner between the inductor and the source, building up charge on the inductor. And then when you throw the switch closed, the magnetic field gets destroyed because of the high impedance that gets added. So the current can't change instantaneously, but the voltage will be whatever it needs to, so it usually spikes and goes higher than what the source is. And then in a buck, when the switch is open, nothing's happening on the inductor and capacitor. It'll be out, but as soon as you close the switch, charge will start to build on the inductor and it'll create a voltage, being whatever it needs to be, which is typically lower than the source.
How big was the solar panel compared to the dime?
Oh, wait,
Oh, do you have one?
way bigger. It's like that-ish.
Oh, okay, half a book.
Yeah, it's relatively overkill for what I needed. 12-volt supply.
Well, there was no requirement that it be 12 volt.
Yeah.
Yeah, so 3 volts would work. right?
Yeah. I just wanted it over 5 volts because if it was lower than the output, then the current would have been lower. And typically USBs are between 150 milliamps to 500 max. So if it was below VN, then it would have been like 100 milliamps, so it would have been like a triple charge. So I wanted to try and keep it above 5 volts. Any other questions?
Had you picked a case or anything to put this in? You're trying to small?
Yeah, no, I want to make the circuit small itself. I mean, relative to the solar panel, it wouldn't matter because there's a lot of space on that, but I'm going to end up pasting it onto the back of attaching it somehow to the back of the solar panel. So you can just carry that around for ease. Another thing is I ran into trouble with my other LTC chip, so I'm not going to be able to use it. I'm going to have to use just a regular buck chip at this point, which sucks. Because it can be really, really low efficiency. It's going to be like 30% or something. Isn't it relative to the input
Okay.
and the output? There's some relation between the output and the input with buck chips, I think.
Well, you could order some chips and pay second-day air. That's the other option. All right. Any other questions?
How long does it take to charge something?
Oh, it'll probably take a while. Because the max that chip can only produce is around 200 milliamps, so it's still a relatively slow charge. So it'll probably take, like 2 hours or 3. It would be like a 45-minute charge or a half-hour charge, something like that. That'd be nice, huh?
So where were you going to use it? Like in your car or
Oh,
something?
you could use it anywhere on the
Yeah.
go. I'd
Yeah.
take it out fishing with me.
Yeah.
When the phone starts dying, I'm out fishing, I don't want to leave. Oh, solar panel. Yay.
All right. Thank you.